Good morning, dear students, and welcome to our course. In the last lecture, we started one of the most important topic of control system that deals with the concept time domain analysis. And we discussed in detail about what exactly the fundamental aspect related to time domain analysis of a system. So, what is time domain analysis or what is analysis? It is nothing but a process in which we know in detail about the system, we know in detail about what type of input we are providing as an excitation to that system, and we are trying to find out what will be the output of that particular system. So the process of finding output, if we know about the system, if we know in detail about the input, that process is known as analysis. And suppose if we provide time dependent input to a system, then in that case, the output or the response generated by that system is also time dependent. That means it is going to vary with respect to time. So, how that response is going to change with respect to time, that deals with the concept of time domain analysis. So, time domain analysis is nothing but a process in which we are trying to find out the response of a system when it is excited by some known standard test input signal, and how that response is going to vary with respect to time. That is important. And then we discussed that the time response of any system we can divide it into two main parts. First one is called as transient, and second one is called as steady state response. Then we discussed in detail about what exactly transient response is. So it is the response generated by a system before it reaches to its final steady state value. And then we discuss some typical points related to transient response, that it may be exponential, that too in it may be overdamped, underdamped, it may be oscillatory, again overdamped or underdamped, or it may be a critical type, neither overdamped nor underdamped. It is denoted by symbol Ct of t, and in order to achieve a final steady state value, system must go through a satisfactory transient period. This is very important, and through this we can identify the stability of a system. And we can also make a comment about the system time constant, and mathematically we can uh, write this equation like limit t tends to infinite, Ct of t must be 0. What is the significance of transient response? Number one, we can define this time constant. Then we can define the nature of response, whether it is exponential or oscillatory, then rate of change of output, and we can also make a comment on system stability using this mathematical equation. And then we discuss what exactly steady state response is. So it is the part of total response that remain once the transient portion is completed. It is denoted by symbol Css of t, and through this we can determine the concept of steady state error. Basically, it is the difference between desired output and actual output. We can also determine the system performance. This is very important. And if we club both transient response and steady state response, we can write them like C of t equals to Ct of t plus Css of t. And suppose if you have a system, to that system if you provide some input in the form of step, it is going to generate some output, and the output will be something like this. So from this figure it is very clear that we have a combination of two main components over here. First one is the transient, and then we have steady state. So this portion is the steady state response. And then we discussed in detail about the concept of standard test input signal. So basically we have four different types of standard test input signal: step, ramp, parabolic and impulse. And then we discussed the answers for these questions, like why only we have four standard test input signal, why they are called as standard test input signal, what is the physical significance of these input signals, and what are the practical examples of those input signal. And finally we conclude that these are nothing but different ways to provide input to any physical system. For example, if you have a physical system like this, in which you have a resistor and you have a source, and your objective is to supply this 20 volt voltage to this particular system. So what are the different possible ways through which you can provide this input to this resistor? Number one, you can close the switch at t equals to 0 plus. The moment you close the switch, entire 20 volt is going to appear across this particular resistor. So that type of excitation is called a step. Then second, close this particular switch and due to some physical arrangement, vary the voltage linearly and gradually. So that type of excitation is called as ramp. Then third, close the switch and then vary the voltage suddenly and non-linearly. Then that type of excitation is called as parabolic. And fourth one is close the switch at t equals to 0 and the very next instant at t equals to say 0 plus, open the switch. So the moment you on off the switch very within a very short span of time, so that type of excitation is called as impulse. So basically we have only four different ways through which we can provide input to any physical system. Hence these type of excitations or these type of methods through which we can provide input to any systems are called as standard test input signal, like step, ramp, parabolic and impulse. The same thing is discussed in case 1, 2, 3, 4, and finally we derive the Laplaces for each one of them. Like if you have a step input signal, mathematically we can write those signals through these mathematical equations, like r of t equals to r for t greater than or equals to 0, and that is going to be 0 for t less than 0. So here this r indicate the magnitude of the signal. That is important. Magnitude of the signal. Suppose if you take r equals to 1, the function is called as unit step function. And if you take Laplace, it will be 1 by s. Then ramp, it is defined by this mathematical sets of equation, like r of t equals to capital R into t for t greater than or equals to 0, and that is going to be 0 for t less than 0. And here this r stand for slope. And suppose if you take r equals to 1, the function is called as unit ramp function. And if you take Laplace, it will be 1 by s square. So this you have to remember, that Laplace of unit ramp is 1 by s square. It is also known as velocity function. And then parabolic, the mathematical expressions to define parabolic is rt square by 2 for t greater than equals to 0 and 0 for t less than 0. And then if you take r equals to 1, it will be t square by 2. And if you take Laplace of this, you will get 1 by s cube as an answer. This function is also called as acceleration function. Then impulse input signal. This is what impulse is. At t equals to 0, signal is available, but t not equals to 0, maybe t0 minus or t0 plus, signal is going to be 0. And the Laplace of impulse is 1. This is very important. This you have to remember. So this portion we discussed in the previous class. Now in today's class, we are going to understand the concept of steady state error. What is the significance of steady state error and how we can define and how we can derive a mathematical expression to calculate steady state error. And we are also going to discuss in detail about the concept of what is system type, what is system order, and if time permits, we can also find different types of error coefficients like Kp, Kv, Ka for type 0, type 1, and type 2 systems. But remember one thing, this portion is very much important as far as GATE exam is concerned, maybe for electrical as well as for electronics and communication engineering students. Because on this particular topic, you may have a theoretical question as well as numerical question. Okay, so let us begin with our today's session. So, what is error signal and what is the concept of steady state error? Now, in order to understand this, let us consider a simple closed loop control system like this. Now, this system is now familiar with everyone. And what are the parameters which I have shown over here? Like G of S indicate forward path gain, H of S indicate feedback path gain. This E of S indicate the error signal, and this B of S indicate the feedback signal. This R of S is the reference input, and the C of S is the control output. And here we have taken a negative feedback system. Now, I hope everyone knows why we have taken a negative feedback system, because we can reduce the sensitivity factor by 1 plus G of S into H of S. Now, mathematically, our objective is to find the expression for this error signal and the expression for this steady state error. Now, what is steady state error? It is basically the difference between the desired output and the actual output. Desired output and the actual output. Desired output means what? The output for which the system is designed. Actual output means the output which is produced by that particular system at that particular instant when it is excited by some kind of input. So, suppose this particular system is designed for output C of S, and suppose if you provide input say R of S, and instead of generating output C of S, this system is going to generate output say C1 of S. So this is going to be desired and this is going to be actual. So the difference between these two is known as steady state error. That's it. Now our objective is to find the mathematical expression to calculate this steady state error and this error signal. How to calculate this? So for that, mathematically we can write C of S is nothing but E of S multiplied by G of S. This I think understood by everyone. The thing is that if you are still having some confusion how to write these equations, just go and check the previous videos. In that I have explained in detail that how we can write these equations. The thing is that if you have a block and if you apply some input to that block, let us consider that the gain of that block is say y, and suppose it is going to generate output say a. So we can correlate this output with respect to input and gain, which is nothing but output is gain multiplied by input. That's it. So if you apply that logic to any block, you can write this equation. Let this will be your equation number 1. In the same way, at summing point, we can write E of S is nothing but R of S minus B of S. That will be equation 2. And B of S, we can write here as C of S into H of S. Let that equation number 3. If you equate equation 2 and 3, so instead of writing this B of S, we can now write this as C of S into H of S. So it will be like this. And then, like a money equation 1 and 4, we can write this. If you solve this, you will get the expression for E of S like this. Let this will be your again equation number 1. So this indicate your error signal. Error signal. E of S is nothing but R of S divided by 1 plus G of S into H of S, where R of S indicate Laplace transform of input. It may be step, it may be ramp, it may be parabolic, or it may be impulse. For example, if it is step, R of s is going to be 1 by s. If it is ramp, it will be 1 by s square. If it is parabolic, it will be 1 by s cube. If it is impulse, it will be 1. So these things you have to remember. Now our objective is to redefine this in terms of steady state error. Or suppose if you are interested to calculate this in terms of time domain, how to calculate that? Because this is the expression for error signal but in frequency domain, right? See, E of s. Now suppose if you want to find this in terms of time domain, how to do that? Now in this case we need to find the concept of final value theorem. So mathematically we can write steady state error as ESS equals to limit t tends to infinite E of t. Why? Because steady state error is nothing but what? The value of error which is available at t equals to infinite. And this we can find out like limit t tends to infinite E of t. Now here from equation number 1 we know the value of error in frequency domain, and here in order to calculate the value of steady state error we required the value of error signal in time domain, that too at t equals to infinite. So then there has to be a relationship between this error signal with respect to this error signal. And what is that relation? It is defined through final value theorem. So by applying final value theorem we can write here as limit t tends to infinite E of t, that is going to be equals to limit s tends to 0 s into E of s. This is what final value theorem is. Now this particular portion, that means limit t tends to infinite E of t, is nothing but your steady state error. So this steady state error is going to be equals to limit s tends to 0 s into E of s. Now from equation number 1 we know the value of E of s. And what is that value? It is nothing but R of s upon 1 plus G of s into H of s. So this entire value now we are going to replace over here to calculate the value of what? Steady state error. I hope this point is clear to everyone. How we have defined this steady state error. Because steady state error is nothing but what? It is nothing but the value of error at t equals to infinite. So when t tends to infinite, whatever the difference between the actual output and the desired output, that is defined by error signal. So the value of this error signal at t equals to infinite is known as steady state error. That's it. The same thing is defined over here. So if you club these two, the modified formula to calculate steady state error is given by limit s tends to 0 s into E of s. Now from equation 1 we can write E of s as R of s upon 1 plus G of s into H of s. Let this will be our equation number 2. Now this equation is very important. This is the expression which we normally used in order to calculate the value of steady state error. And from equation number 2 it is very clear that the value of steady state error depends on following factor. Number 1, it depends upon the type of reference input signal, that means R of s. Because I told you that what is R of s? R of s indicate the Laplace transform of input. Now we have four different types of standard test input signal. It may be stem, it may be ramp, it may be parabolic, or it may be impulse. So based on that we have different values for R of s, and based on that we have different values for steady state error. Number 1. Number 2, it also depends upon the nature of open loop transfer function. So what is open loop transfer function? The product of forward path gain and the feedback path gain. That means G of s into H of s. This is known as open loop transfer function. सो ओपन लूप ट्रांसफर फंक्शन पे भी आपका स्टेडी स्टेट एरर जो है वो डिपेंड करता है, दैट इज इम्पोर्टेंट। तो ओपन लूप ट्रांसफर फंक्शन अगर चेंज होगा तो आपका स्टेडी स्टेट एरर भी चेंज होगा, या फिर जो रेफरेंस इनपुट सिग्नल है अगर वो चेंज होंगे तो आपका स्टेडी स्टेट एरर भी चेंज होगा, दैट इज इम्पोर्टेंट। Now, in gate, you may have a questions like this: on what factor steady state error depends. And options are like it depends upon the nature of input signal, it depends upon the nature of open loop transfer function, it depends upon both A and B, or none of above. Answer is both A and B. Now let us try to find out how this steady state error is going to change if we change the reference input signal. Like if you vary R of S, then based on that how the steady state error is going to change. Now we know that the mathematical expression to calculate steady state error is like this. Now case 1. Now what we are going to consider is that the reference input signal which is available with us is nothing but unit step function. And the moment I take unit step function, we know that the Laplace transform for unit step function, which is nothing but Laplace transform of 1, is going to be 1 by s. So what we are going to do, instead of writing this r of s, now we are going to replace this r of s by 1 by s. And then in that case we are trying to find out the expression for steady state error. So if you apply that logic and solve for ESS, this S and S will get cancelled, and finally we have this modified version of steady state error. So steady state error is going to be 1 upon 1 plus limit s tends to 0 g of s into h of s. Now this portion, limit s tends to 0 g of s into h of s, we are going to indicate by some other component that is called as position error coefficient, indicated by symbol kp. So kp is limit s tends to 0 g of s into h of s. So this is very important. This is called a static positional error coefficient, and hence the expression to calculate steady state error when the input excitation is unit step is given by this mathematical equation. ESS is nothing but 1 upon 1 plus Kp, where Kp is limit s tends to 0 g of s into h of s. This formulas you have to remember, because in gate, based on this formulas directly you have a numerical for 2 marks. Like system is given to you, they also mention that what type of input they apply as an excitation, and your objective is to calculate the value of steady state error, maybe for type 0 system, type 1 system, or type 2 system. In the coming portion we are also going to discuss what exactly type is and what exactly order is, but for time being let us consider that this is the formula to calculate steady state error when the system is excited by unit step input signal. Please note down these formulas because these are very very important formulas, and we are discussing one of the most important topic of control system, that to time domain analysis. Once you have done with this, then case number 2, because we have 4 different cases or 4 different types of standard test input signal, and we are trying to analyze that how this value of steady state error is going to change if you change the nature of input signal. Now instead of taking unit step, now we have taken unit ramp, and let us try to calculate how this ESS is going to vary. So the moment we take unit ramp, R of s is going to be 1 by s square. And again, if you apply that logic in equation number 2, what is that equation? It is going to be like limit s tends to 0, s into R of s whole divided by 1 plus g of s into h of s. This is your ESS. So the moment you take this R of s is 1 by s square, it will be something like this. Again, if you solve this, you will get this. If you modify, further solve, you will get this. And finally, if you separate numerator denominator, it will be like 1 upon limit s tends to 0, s into g of s into h of s. Now this particular term is known as kV, velocity error coefficient. So in case of unit step, we have positional error coefficient Kp. In case of unit ramp, we have velocity error coefficient. So the steady state error is this 1 upon kV. That's it. This is the expression to calculate steady state error when the system is excited by unit ramp input signal. This you have to remember. In the same way, suppose if you take unit parabolic function, then what will happen? R of s is 1 by s cube. From equation number 2, it will be like s into R of s upon 1 plus g of s into h of s. So R of s is 1 by s cube. So this and this will get cancelled. You will get a square over here. And if you further solve this, you will get this as an output. Now here we can define this as limit s tends to 0, s square g of s into h of s. This is going to be your Ka, which is called as acceleration error coefficient. And hence the mathematical formula to calculate steady state error when it is excited by, or when the system is excited by unit parabolic input, is nothing but 1 upon Ka, where Ka is your static acceleration error coefficient. So these formulas are very important and you have to remember this. I hope this point is clear to everyone. So first portion of dependency of steady state error on reference input signal we have done. So finally what we conclude, that if we have unit step, we have Kp, and the expression to calculate steady state error is 1 upon 1 plus Kp. If you have unit ramp, we have velocity error coefficient, and the expression to calculate steady state error is 1 upon Kv. And suppose if you have unit parabolic, we have Ka, acceleration error coefficient, and the value of steady state error is 1 upon Ka. That's it. Now what is Kp? Kp is limit s tends to 0, g of s into h of s. What is Kv? Limit s tends to 0, s into g of s into h of s. And what is Ka? Limit s tends to 0, s square into g of s into h of s. Once you have done with this, now let us try to understand what is the effect of variation of open loop transfer function on steady state error, because we discussed from equation number 2 that steady state error depends on two factors. Number one, it depends on the nature of reference input signal, that is R of s, and then it also depends on open loop transfer function, which is g of s into h of s. So in the previous section we discussed in detail about how the value of steady state error is going to vary if you change the nature of input signal. Now we are going to understand. Now suppose if you change the nature of open loop transfer function, or you can say the type of system, then corresponding to that how the steady state error is going to vary, that we are going to learn. Now the open loop transfer function of a system we can define as a product of forward path gain and a feedback path gain. Hence mathematically we can write open loop transfer function like this. So it is going to be like k, where k indicate the overall gain of the system, then 1 plus sta, 1 plus stb, and so on, whole divided by s to the power n, in bracket 1 plus st1, 1 plus st2, and so on. So this ta, tb are responsible to form the zeros of the system, whereas this t1, t2, and so on are responsible to form the poles of the system, and this indicate the overall gain of the system. Overall gain of the system. And here s to the power n, this n indicate how many number of poles are available at origin. Number of poles at origin. I hope this point is clear to everyone. This we already discussed when we discussed the concept of transfer function. So what is transfer function? Basically it is nothing but the ratio of Laplace of output by Laplace of input, or it is simply the ratio of two polynomial expression. Your numerator, and here we have denominator. If you equate numerator to 0, we can identify the concept of zeros. If you equate denominator to 0, we can identify the concept of what? Poles. So if you equate s to the power n to 0, we can identify that how many number of poles or how many number of complex frequencies are available at origin. So those number of complex frequencies are nothing but poles at origin. That is important. So k is overall gain of the system, 1 upon Ta, 1 upon Tb with negative sign. That means in order to calculate the value of zeros, if you equate this particular term to 0, like 1 plus s Ta equals to 0. So we can calculate the value of s. S is going to be minus 1 upon Ta. So this will be the 0 of the system. In the same way, if you are interested to calculate pole, you have to equate this term to 0. So equate this term to 0, it is going to be like s equals to minus 1 upon T1. So these are zeros and these are nothing but poles. That's it. Here and indicate number of poles at origin. So this is very important. This is the general expression of open loop transfer function for a system. This you have to note down. What is K? What is 1 upon Ta, 1 upon Tb? Then what is 1 upon T1, 1 upon T2 with negative, and what is capital N stand for? If we are done with this, now let us try to define the concept of type of system. So type of systems are nothing but how many number of poles are available at origin. That's it. So type of a system is nothing but how many number of poles are available at origin. That's it, of an open loop transfer function. For example, the number of poles at origin possessed by an open loop transfer function is basically classified like n equals to 0. That means it is called as type 0 system. So the moment you put n equals to 0, that means the expression is in this expression indicated by equation number 3. Here if you put n equals to 0, the moment you put n equals to 0, s to the power 0, this is going to be equals to what? 1. This is very important. And here from this we conclude that there will be no pole available at origin. No pole at origin, because n equals to 0, or what is n? Number of poles available at 0. That's it. So same thing is mentioned over here. The moment you take n equals to 0, there will be no pole available at 0, or no pole available at origin, and that type of systems are called as type 0 system. In the same way, if you take n equals to 1, that means one pole is available at origin. This is called as type 1 system. If you take n equals to 2, two poles are available at origin. If you take n equals to n, n poles are available at origin, nth type system or type n system. So equation number 3, it is very clear that the value of open loop transfer function depends on the type of system, and hence we can also vary the value of steady state error, because we know the general expression for steady state error. Steady state error is nothing but limit s tends to 0, s into r of s whole divided by 1 plus g of s into h of s. Okay, and we have discussed in detail about how this steady state error is going to vary due to change in r of s. Now we are trying to find out how this steady state error is going to change due to change in this open loop transfer function. And recently we came to know that the value of this open loop transfer function is going to vary due to change in type of system. Type of system. That means if you vary the type of system, open loop transfer function is going to vary. And the moment open loop transfer function is going to vary, automatically steady state error is also going to change. So now we are going to find out how this steady state error is going to change due to change in the type of a system. That is very important. So let us try to examine them one by one. So for example, if you take type 0 with unit step input, how this is going to be? So for type 0, the open loop transfer function is like this, because here s to the power n, n is nothing but 0, s to the power 0 is going to be 1. That's why this term is going to be 1. So 1 into this. Now we know that in case of unit step input signal, we have kp. So it is given by limit s tends to 0, g of s into h of s. So what we are going to do, we will replace this g of s into h of s by this particular expression. That's it. And if you try to solve this limit by putting s equals to 0, you will get kp equals to k. That means in case of type 0 system, for step input excitation or unit step input excitation, the value of kp, which is nothing but positional error coefficient, is always going to be equals to the overall gain of the system. That is important. And we can calculate the value of steady state error too. It is nothing but 1 upon 1 plus kp, but kp is k, so it will be 1 upon 1 plus k. So this formulas you have to remember. Directly based on these formulas you can have numericals on gate, in gate. So for type 0, the value of kp is k and the value of ess is 1 upon 1 plus k. In the same way, for type 0, again, if you change the input from step to ramp, let us try to find out the value of uh, your kV, because in case of ramp we have velocity error coefficient. So it is going to be like s into g of s into h of s, and we need to take limit of that, limit s tends to 0. So the moment you take this and replace this g of s into h of s by this expression and try to calculate, the value of kV is going to be 0. And the moment kV is 0, you can calculate ess, that is steady state error. It is going to be like 1 upon kV. It is going to be 1 upon 0. It is going to be infinite. So what is the meaning of this? That means in case of type 0 system, if you excite that particular system with unit ramp input signal, the value of error or steady state error is infinite. That means type 0 system is not designed to work for unit ramp input signal. That means if you are dealing with a kind of system where that system do not have any pole at origin, that means it is type 0 system, then in that case, if you are interested to analyze the behavior of that particular system, don't take unit ramp input signal for that, because the moment you take unit ramp input signal and provide as an input excitation to that particular system, the value of steady state error is going to be infinite, ideally, theoretically, as high as possible. So we cannot determine the behavior of a system or type 0 system with unit ramp input signal. That is important. In the same way, if you have type 0 and if you take unit parabolic input, same procedure. The thing is that in case of unit parabolic, we have acceleration error coefficient indicated by symbol Ka, and the expression is limit s tends to 0 s square g of s into h of s. Now again replace this g of s h of s by this expression, solve, you will get Ka 0. Again, if you calculate steady state error, it is going to be infinite. That means for type 0 system, if you take unit ramp, the value of Kp is K, and steady state error is going to be 1 upon 1 plus K, which is finite. But if you take unit, this is unit step up, this is unit step. But if you take unit ramp, the value of Kv is going to be 0, and steady state error is going to be infinite. And if you take unit parabolic, the value of Ka is going to be 0 and steady state error is going to be infinite. That means type 0 system are only designed to work for unit step input excitation only, because in that case the value of steady state error is finite and we can have the mechanism to control that steady state error. This is very important. So in gate you may have a question like that. In case of type 0 system, if it is excited by say unit ramp, what will be the value of steady state error? So directly you can take the value of steady state error as infinite. What is the value of positional error coefficient when it is excited by unit step? It will be k. Now let's switch the type of system. So instead of taking type 0, now we need to take type 1, and again apply the same topology. If you take unit step, what will happen? If you take unit ramp, what will happen? If you take unit parabolic, what will happen to the value of error coefficients and to the value of steady state error? The procedure you need to repeat once again. Again for type 1, the value of n is going to be 1. because in this case we have one pole at origin. In type 0 we don't have any pole. Now in type 1 we have one pole at origin. That's why if you put n equals to 1, s to the power 1 is going to be s. See, here we have s, one pole available at origin. Now need to take, if it excited by unit step, what will happen? The value of positional error coefficient is limit s tends to 0, g of s into h of s. Solve this, you will get this as infinite. And if you try to calculate the value of steady state error, it is going to be 0. This is very important. That means if you have type 1 system, and to that system if you apply unit step input as an excitation, the value of steady state error is at minimum possible value. Ideally it is 0, which is the desired condition. I hope this point is clear to everyone. Then for type 1, if you take unit ramp and again apply the same logic, calculate the value of kv, velocity error coefficient, you will get this as k. And if we try to calculate the value of steady state error, it is going to be 1 upon kv, which is 1 upon k. So in case of type 1 system, the value of steady state error is 1 upon k, which is a finite value. But for type 1, if you take unit parabolic and try to calculate the value of ka, this is going to be 0 and steady state error is going to be infinite. That means type 1, for example, if you have a system that is type 1, and suppose if you are interested to find out the behavior of that system, and you need to decide that whether you need to take unit step, unit ramp, or unit parabolic, then if you prefer unit step, then in that case the error of the signal is going to be 0. But if you prefer unit ramp, then in that case the value of error is 1 upon k. But if you prefer unit parabolic and try to identify the behavior of the system, the error is going to be what? Infinite, which is undesirable. Hence type 1 system is designed for working on unit step as well as unit ramp. That is important. In the same way, we can do the same topology for type 2. Now in type 2, the value of n is going to be 2. That means we have two poles at origin. That is important. That's why here we have a square. See, again try to calculate the value of kp, kv, ka and ess in each case. Like if you take unit step, then what will happen to kp and what will happen to ess? Kp is going to be infinite, ess is going to be 0. Again for unit ramp type 2, kv is going to be infinite and ess is going to be 0. Now this is important. And if you take unit parabolic for type 2, ka is going to be k and ess is going to be 1 by k. That means if you have a system that 2 of type 2, that means 2 pole available at origin. So this system is designed for unit step, unit ramp as well as unit parabolic input signal, because in each case the value of steady state error is 0 or you can say finite. If you take unit step, unit ramp, the value of steady state error is 0, and if you take unit parabolic, the value of steady state error is finite. It is not infinite, which is desirable condition. So these points are very very important. All the cases which we have discussed so far, like what is the value of steady state error if you change the nature of input signal like kp, kv, ka, and then what is the value of kp, kv, ka followed by ess for type 0, type 1, type 2 for different types of input excitation. That is very important, and based on this concepts you have so many numerical direct formula based or so many theoretical concepts that may ask in gate exam. So finally, what we conclude is mentioned in this table. This is very important. So whatever the cases which we have discussed so far, all the cases are mentioned in this table. So this table is a summary of what we have discussed so far. So if you take input like unit step, unit parabolic, or unit ramp, this is unit ramp and this is unit parabolic. We know that the Laplace of unit step is 1 by s, Laplace of unit ramp is 1 by s square, and Laplace of parabolic is 1 by s cube. And then for type 0 system, the value of error coefficients in different cases, like for type 0, if you take unit step, the value of kp is k, and the error coefficient is finite, which is 1 upon 1 plus k. But the moment you apply unit ramp or unit parabolic input to type 0, the value of steady state error are infinite, which is undesirable. So we can conclude that type 0 systems are not designed to work for unit ramp or unit parabolic. That is important, because the moment you take unit ramp or unit parabolic as an excitation for type 0 system, the value of steady state error are going to be very large. But if you take type 1, so for type 1 system, the value of kp is infinite and steady state error is going to be 0. Or if you excite the system by unit ramp, the value of steady state error is 1 upon k, which is finite, and we can have a flexibility to control that. But if you take a unit parabolic as an excitation for type 1 system, here see the value of steady state error is infinite, which is undesirable condition. That means type 1 system, if you have, and suppose if you are interested to find out the behavior of this particular system, go for either step input excitation or ramp input excitation. Don't go for parabolic, because the moment you take parabolic input excitation to check the behavior of type 1 system, the value of error signal is going to be infinite, which is undesirable. But if you take type 2 or higher order, or you can say higher type system, the value of steady state error is going to be 0 or finite, which is desirable condition. So this table is very important, and based on this table, you may have various types of theoretical as well as numerical questions that may ask in GATE or any competitive exam, specifically if you are preparing for the control system part. So my suggestion is, whenever you are preparing for any competitive exams that do in technical domain for control, don't miss this particular summary. You may have two, three, or even more than that theoretical as well as numerical questions on this particular table. So I want everyone to please note down this. This is what the final conclusion, how we can calculate the value of steady state error and how the steady state error is going to vary if you change the nature of input excitation signal and the type of system. So what is type? It is simply how many number of poles are available at origin. If type 0, that means no pole is available at origin. If it is type 1, one pole is available at origin. If it is type 2, two poles are available at origin. That's it. So same thing is mentioned over here. Whatever the points which I have discussed so far are mentioned in the point form. So the observations which we have drawn from the table is for type 0, the ramp and the parabolic inputs are not acceptable. For type 1, parabolic is not acceptable. And for type 2, all type of signals are acceptable because the value of steady state error is either 0 or finite. The finite steady state error varies in inversely proportional to forward path gain. That means K. See, in all the cases, if you see the expression for steady state error, see, The expression for steady state error for type 0 for unit step, it is 1 upon 1 plus k. So k is available in the denominator. In the same way, the expression for steady state error for type 1 system, that too for ramp input excitation, it is 1 upon k. Again, k is in denominator. And the expression for steady state error for type 2, that too when you are excited that system by unit parabolic, again the expression is 1 upon k. So k is available in the denominator. So from this it is very clear that the value of steady state error is inversely proportional to the overall gain of the system. That means if you increase the value of gain, automatically steady state error goes on reducing. That is the reason in most of the control system designing aspect, we want to increase the value of this gain k as high as possible. The moment you increase the value of this gain k, automatically without doing anything, the value of steady state error goes on reducing. This is very, very important. Based on this, you may have various types of theoretical as well as conceptual questions in gate exam. Now to solve numerical on whatever the topics which we have learned so far. So this portion we will continue in the next class, but I just want you to note down the statement for this numerical. In this case, we have an open loop transfer function of a system which is given to us, and it is g of s into h of s is nothing but 2s square plus 3s plus 20, or you can say 2 in bracket s square plus 3s plus 20 whole divided by s in bracket s plus 2, then in bracket s square plus 4s plus 10. So this is the open loop transfer function which is known to us, and our objective is to determine the value of static error coefficients and steady state errors for the inputs given to us. In case 1 we have input like 5, then 40, and then 40 square by 2. So here our objective is to calculate error coefficients like kp, kv, ka, as well as the value of steady state error like ESS in these cases, because this 5 is nothing but your unit step. It is not unit. Now here the magnitude of that step function is 5. Okay, and this is your 40. This is your ramp, and this is your parabolic. So your objective is, suppose if you take this as an input and provide this input to this particular system, what will be the value of your KP and what will be the value of ESS for this particular system. So whatever the things which we discussed so far, you need to apply those logics over here to solve this numerical. So try this as an homework. Today we will stop at this particular point, and tomorrow we will start our topic from the same point. Like first we will solve some numerical on the calculations for steady state error and error coefficients, and then we will uh, discuss the concept of order of system followed by time response analysis. Okay, thank you.